When we look up on a dark night, we see a sky filled with stars. The light from a star, like the light from a flashlight or a lightning bug, is one form of electromagnetic radiation. Light is formed of waves, and different colors of light have different wavelengths. Red light has a longer wavelength than blue light, but the colors we see with our eyes represent only a tiny piece of the story. The electromagnetic spectrum spans from radio waves, with wavelengths longer than a car, to gamma rays, with wavelengths smaller than the nucleus of an atom. We can learn a great deal by looking at things with our eyes or with optical telescopes, but different parts of the spectrum may reveal a very, very different picture. Sound is a form of wave as well. Though it is different from light, it can help us understand why astronomers use everything from radio telescopes to gamma ray detectors to study the skies. Sound waves with long wavelengths are heard as low pitches. Short wavelengths are heard as high pitches. What if we think of sound from the lowest key on a piano as the longest radio wave, and that from the highest key as the shortest wavelength gamma ray? What would music sound like if we only listened in the range that would correspond to visible light? Igor Levchinsky, a renowned pianist and also a physicist, explains.
The electromagnetic spectrum spans about 20 decades in wavelength. The longest radio waves are about 100 billion times longer than the shortest gamma rays. Now, visible light makes up just a tiny fraction of the spectrum. So if we were to map the electromagnetic spectrum onto the piano keyboard, the visible light would correspond to just 2 keys. The images that could be seen by a Hubble Space Telescope will correspond to these. And the Chandra X-ray Observatory covers higher frequencies, but still just a small fraction of the piano. One of my favorite pieces of music is Chopin's Polonaise in A-flat. Now, suppose that I could only use the keys on the piano that correspond to the visible range. How would the piece sound? Clearly something is missing here. Now let's hear the same thing as seen by a radio telescope. Well, that's certainly different, but not exactly catchy. So why don't we try it with the Chandra X-ray Observatory? And finally, the Fermi Gamma Ray Observatory. So by now you're probably wondering how this could possibly be one of my favorite pieces. But now let's bring out all of our telescope and see what it sounds like. If we could observe across the entire spectrum, the piece begins to sound a little bit more impressive.
Astronomers use specially designed telescopes to be able to study objects at many different wavelengths. What each telescope reveals can be very different. Pat Slane, an astrophysicist who studies stellar explosions, explains.
The Crab Nebula is one of the most studied objects in the sky. It was first identified by Chinese astronomers in the year 1054 as a bright exploding star. You can actually see this object with a pair of good binoculars at a dark site. And observations with a larger optical telescope show a fuzzy oblong object with a series of complicated filaments. Observations with radio telescopes show us something similar. There's an oblong structure. It has filamentary elements to it as well. But there's a central compact source. Left by the exploding star is a compact neutron star spinning about 30 times per second and generating a wind of energetic particles that energize the nebula. Gamma ray observations show us emission from the nebula as well, although most of the emission comes from the compact pulsar in the center. When we look at the Crab Nebula with the Spitzer Infrared Telescope or the Hubble Space Telescope, we see that network of filaments showing us where the wind from this pulsar is interacting with the inner portions of the star that exploded. Observations with the Chandra X-ray telescope show emission from the neutron star, it's very bright, but also a complex series of rings and jets surrounding it where the wind from the pulsar is actually joining the interior of the nebula.
Through studies of the Crab Nebula across the electromagnetic spectrum, we now understand that it is powered by the Crab pulsar, a highly magnetic neutron star that, through its rapid rotation, acts like a cosmic generator. The pulsar accelerates particles to extremely high energies, and this outflow of particles streams out into relic material from the interior of the star that exploded in 1054, forming the system. The rings and jets seen in X-rays, which can be observed to vary on timescales of weeks, mark the regions where the pulsar wind first enters the nebula. The network of filaments seen in optical and infrared observations is produced by the outer nebula sweeping up material enriched in heavy elements through nucleosynthesis during the evolution and subsequent explosion of the progenitor star.
The Crab Nebula is the best studied pulsar wind system. If our understanding of the Crab was limited by what we could see with our eyes, our knowledge of these systems would be meager indeed, and the same could be said of most other astronomical systems. Our first observations draw us in, sort of like a few twinkling notes on the piano, but to really appreciate the beauty and wonder of these objects, we really have to hear the entire piece.